Hi guys, Mr. Ford here. Just wanted to go over a few things about your practice exam. You can see the grades are in Schoology. There's two different types of grades. There's the one that's in your gradebook page. It's like the overridden curved one according to the AP guidelines that we've done for the midterm and if there was a real mock exam. If you go into the Schoology quiz, you should be able to see for each question the points that you were awarded out of 12 or 7. So that was like your raw score. So feel free to look at that and see how you did raw. A couple things I noted before we get into going over the solutions. The biggest thing that I saw, biggest point loss, was simply just answering the question. It wasn't the physics that you did or did not understand. It was you did not directly answer the question you were asked. So that's the biggest thing. For some, that was a big point loss. So if it's saying, does it increase, decrease, or stay the same, and you simply just says it changes, you did not answer the question. And a lot of the rubrics state that no points are awarded for the increase or decrease, but if you are not explaining that aspect, you're not going to be awarded the points as well. Let's see. For these two, you could have seen where typing your answers or typing in a Word doc and copying and pasting, not simply just taking a picture, may help out on the real exam next week. If there's obviously there's not going to be any drawing or sketching like there was for this one. But if there's no math or lengthy math, typing right into their platform might be the fastest way. There's several students, more than several, probably a third of the students that took the exam had an issue with how to submit, not being able to submit pictures, submitting a link for a Google Doc, which was not a way to submit, not writing clearly. I don't know if I mentioned taking a bad picture. The lighting wasn't good. Or just bad handwriting. I couldn't read what they wrote, or it was very difficult for me. I had to download it, zoom in, and try and figure out what words meant. So instead of handwriting a paragraph or a sentence or two response, it might be better just to type it in there. That way you don't have to worry about it. So again, follow the rules, how to submit, when to submit. Timing was a big issue. Some people said they waited until the last minute to submit, and I said use that 5 minutes. Now you didn't have a flashing red timer pop up like you will on Thursday, but do not underestimate the time it takes to take a couple pictures, put this here, put that there, click a couple buttons. I mentioned handwriting. If you're like me and you know you have bad handwriting, like I said, take your time, make sure it's legible for other people. This is essentially like a job. Like this could be earning you money potentially. Maybe not in getting you credit for not having to take a physics course, but getting you out of maybe a general level course, which may cost a few $100s. Picture quality we mentioned. Correct symbols. So refer to your equation sheet for the correct symbols. So in the one question it did say to represent radius with RA because it was the radius of pulley A. But then later on in a problem or in another question, don't use that same symbol. Don't use a capital R. They use on the equation sheet, correct me if I'm wrong, a lowercase r to show radius. If you're not sure, make a key for yourself. Some people were putting a capital T for torque. Capital T is period. Lowercase t is time. That tau is a little bit different. If you're not sure how to draw it, look at your equation sheet or even mention that this is torque, like write out torque. Something across the board, a lot of you do not show all work. If it's asking you to derive an equation, you need to go start to finish. Everything from that equation sheet that you used, you need to state. You cannot skip steps because deriving an equation is essentially, you're telling the grader, like you're teaching them. Like you're going from this step to this step to this step. Let's see. I think that's pretty much all I note as big things that might cost people, like a 4 versus a 5 or a 3 versus a 5, is answer the question that's being asked of you. Follow all the rules that they're asking you to submit by. All right, so now we're going to go over each question. each part of one. I'm going to tell you how many points were available, how many I awarded if you did this or that. If you have specific questions, send me a Schoology message or sign up for office hours next week. I'll post at some point over the weekend your work for the next 2 weeks probably, so you can budget your time. There is going to be a little bit of time because you are AP students, so you are above and beyond, but AP teachers are going to go, and hopefully other teachers go a little bit lighter, knowing that you may have all these exams to study for, prep for, and also take this week and next. So here we go. Okay, so the first one, this is the QQT, or the quantitative qualitative. You saw how there was not necessarily numbers per se, but they were looking at things increasing, decreasing, and deriving some things. So the first part A, you were asked to determine which pulley, sorry, let me read the question. Which one will complete its revolution first? So obviously this is a rotational motion problem where pulley A would be a uniform cylinder. Pulley B would be like a hollow one. So in pulley A, the mass, since they are the same mass, is equally distributed. Pulley B, that mass is focused on the outer part. So the further away that mass is, the more rotational inertia that it has. Keeping in mind what rotational inertia or moment of inertia is. It's resistance to change. So since these things were starting at rest, whatever one is more resistant, meaning more keep in mind it's like rotational mass, it's going to accelerate less. So pulley A, less rotational inertia, easier to accelerate. So that means its acceleration will be greater, therefore make that one revolution in less time. So for part A, you got your, let's pick a good highlighter color. Let's go green here. Good green? No, it's not good green. Let's go blue. So here, oh, that's why it looks weird. Sorry. Let's make it bigger. There we go. So for just mentioning that it was pulley A, you got your point. So this was one of the ones where you pretty much had a 50-50 shot. Or I'm sorry, 1 out of 3 chance, because there was that other option of both having the same. Sometimes you will, like for this one, you don't know whether you get a point for that or not. So it's kind of a weird scenario to be in. So you got 1 point for stating that. The second point was in your explanation. You had to mention that the A had less rotational inertia. Rotational inertia was the key, or moment of inertia was the key word that you had to mention. So as long as you mention that, and less rotational inertia meant an increase in, or more acceleration, which was less time to rotate. I didn't finish writing rotate there. So that was the second one. Part B, you had to derive an equation. Now this is where thinking linearly might be advantageous. So think of this, even though we have established this as a rotational problem, think linearly. What did they give you? They gave us, we're looking for the time it takes. We know 1 revolution. Force, rotational inertia, so essentially we know the mass and the force. So it's kind of like knowing time, mass, distance, and force. So a lot of people want to start off the problem looking through Newton's second law for rotational. I don't necessarily, and then you get stuck though. A lot of you guys started to go through and try and break down acceleration into change in velocity per time. The issue with that is there's no mention of velocity. So we don't know what that velocity was that it got up to. So we wouldn't be able to calculate it. And a little hint, they're not asking us to express our answer in terms of that. So it's going to be hidden in other parts of the problem. So we're going to start with kinematics. So just like I said, if we had the displacement, we had knowing that that initial velocity was 0 and it would cancel out. We're asked to express it in terms of or I'm sorry, that's the only other thing, is it might be a little tricky not seeing that acceleration there. But it's easier to see that they are asking for time. Time is a lot of times where you're going to, no pun intended, in kinematics get those answers for time of something. So we run into a problem. We see that it was 1 revolution, so rotationally 1 revolution is 2 pi. Is we don't know acceleration. So this is where Newton's second law comes in. So we make that statement, Newton's second law for rotation, torque equals I alpha. It's kind of like F equals ma. And we go through and derive that as equal to A in the terms that they are expressing, or asking us to express. So we know torque is force times radius. We don't have to worry about sine theta because it's perpendicular to the lever arm or the moment arm, or the radius, if you will. So we define it as they asked us to, the force from the spring scale, the radius of the pulley will be equal to I, or rotational inertia, of pulley A, and then we have alpha. So I went and set that equal to alpha, so then I just had to go plug that over in. So I took this and plugged it in for A, and then got my equation. So then after I have this part here, all I have to do is do some algebra. So 2 pi divided by half. Keep in mind, dividing by half, you multiply by the inverse. So that's where the 4 pi comes from. And then multiplying the other variables over appropriately, and then solving for t, not t squared. So there were some people that had issues with the algebra with that 2 pi and some things that way. Some people didn't see the second law application of it. But again, you're not going to get everything perfect all the time, even if you wind up with a 5. So everything that's in green, you were given a point. So there were 5 points total. So according to how we did it, you got 1 point for mentioning kinematics, a kinematic equation that would help you solve for it. You got 1 point for mentioning that 1 revolution, 1 rotation was 2 pi. You got 1 point for addressing Newton's second law being applied here. Another point for understanding what torque was. And then, of course, 1 for your final full answer. So that was kind of a big chunk of that 12-point question. So that was BI. So this is II. So they're asking you, is anything different? So this is almost like a self-check for you. Like, you know, why are they asking me this? Is something the same? Why is it the same? Something different? Why is it different? Going back and looking at our work. So you had to get, for this one, for the II, to get that point, it had to be yes. You couldn't say no. So yes, you know this by looking at your equation that you derived. So the only difference in that pulley B, right, is that the one we're looking at? Yeah. Sorry, I'm reading the question again. Oh, no, sorry. We're not changing anything. It's just looking at conceptual versus like a math derivation. So in here, we reasoned A was less rotational inertia. So if that's smaller, it should go faster. And that makes sense as well, because if rotational inertia right here in our equation, that's proportional to time. So if rotational inertia was less, it would take less time. So you just need to mention that to get that point by saying yes, and then also including the only difference was the rotational or inertia, which was I. I like that color a little bit better. Part C, this was looking at pulley A and saying, like, we don't have the spring scale anymore, we're just hanging this mass M, and talking about some other variables. So we had to say what happened to the net torque, the angular momentum, and how we figure that out. Notice it says briefly describe how you arrived at your answer. You don't want to simply do a math equation and say, see equation on the left or see equation above. You want to explain it. You can use an equation in your explanation, but make sure you are describing. For C, you got no point for checking the right box, essentially. You got your point for checking the right box, and then also the explanation. So for net torque, there was no change as the mass falls, as the pulley starts to spin and the cord goes down. And that's simply because you can look at the equation to start. Torque is force times radius. So where that pulley or rope is being attached is not changing. The force is not changing. The force is still the same hanging mass, whatever that thing weighs. So same mass, same radius, or same force, same radius, no change in torque. What they did note, though, is you got no point for saying that the tension in the cable is equal to the weight or the force of the mass. Because keep in mind, with rotational motion, the tension and the weight is not the same because there is another force involved. We're looking kind of like at net scenarios. Angular momentum. So it increases. Hopefully we could just think through this and see that it would keep going faster and faster and faster. Because if there is that net force or net torque, you're going to have an overall acceleration, meaning you're always going faster. So looking at momentum, L being momentum, I is rotational inertia, that has not changed, and W angular velocity. So if our angular velocity is increasing, so would our angular momentum. Part D, we are now looking at a different scenario where in the first picture we have the cord is all coiled up, and then as it goes out, it goes in decreasing the radius. So the net torque is going to decrease, and the reasoning is, so this one was another one, you got your 1 point as long as you had the correct reasoning. I'm sorry, the net torque decreases because the radius decreases. So that was the easy part. They get tricky in the next one, and they got some of you guys and girls. Rotational kinetic energy. So remember, there is linear and there's rotational. So rotational, we're looking at I omega squared. So the rotational inertia is decreasing. So that's going to lead a lot of people to think, okay, well, the kinetic energy is going to decrease. So there's two ways to look at it. One, in this scenario, we're going from having all gravitational energy to kinetic. So midway down when this thing is falling, all of a sudden it's not going to go back up. You got to think of where that energy is coming from and going to. So that's one little hint. The biggest hint is seeing that this thing is not going to slow down. Its acceleration is going to slow down. It's going to decrease. But it's still going faster. So that's like driving in a car. You slam on the gas, you're going to accelerate really quickly. You take your foot halfway back, not off the gas, but the gas pedal is halfway depressed, you're still going faster and faster and faster. The rate at which you're going faster is not, though. And this is assuming we're ignoring friction and air resistance. So seeing that we're still increasing our velocity, the kinetic energy is still going to go. So you got your 1 point for mentioning it, maybe using an equation, or saying that the rotational acceleration decreases, but is still going faster and faster. That would be your reasoning. So that was all of your points. Go back and look in green, see where you might have been awarded or lost points. If you have any questions, let me know. Question 2 was the general paragraph one, the one with the plunger. Only worth 7 points, I believe. Yeah. So this was 5 and 2. So the first part, they're asking you to look at each stage and tell what's happening to the speed of the center of mass. So keeping in mind, any center of mass problem, we didn't really go into that in detail, but what was the answer that we always said it was? The speed or velocity of the system or of the center of mass is always constant. So that was only apparent in earlier units when we were looking at momentum, collisions, right? So things were moving in the beginning and not moving in the end. So it was like before and after a collision. So the first part of this problem, from A to D, there are no collisions. Or I'm sorry, A to E. A to E. There are no collisions. So the first part of it is just looking at the speed of the block number 1. I think it's block 1, yeah. So in the beginning, let's see, sorry. Yeah, so we only see friction at part C. From C to D, there's friction. So from A to B, we're going to see a force being applied. So when there is force applied, when no friction, there is going to be an acceleration. So it was at rest, so hopefully we had 0. So you got a point for saying it started at rest. 0 speed, because that's what we're looking for. Then it accelerated, meaning it changed its speed. Now we are only looking at constant acceleration, so on a speed time graph, we're going to be a constant increase in speed or a constant acceleration, so it's going to be a straight line. So if you had a curved line in there, you didn't get your point. Then from B to C, that's when the force is no longer being applied to the block, so it's moving at a constant speed, no acceleration. You're perfectly horizontal straight line from A to B, or sorry, B to C. You got your next point. Then as it comes to C and D where there's friction, well, what does friction do to things? It slows it down. It is a constant force because nothing is changing. It's not mentioning any changing in friction. So constant force is constant acceleration, meaning a linear change in velocity or speed. So that should be a straight line. If it's not straight line, you didn't get that point. Now, this is where the teacher and me kind of came out when I was grading. Some people had curves and it was very apparent that it was a curve. Some people, it was like, are they just bad at drawing straight lines? So you won't be having that on this exam this year, but in future exams, if it's not apparent and you are allowed to use a straight edge, which you are on the real AP exam, and you choose not to use that, and the person grading it was like, oh, this doesn't look like a straight line, and they had a straight edge, so I'm not going to award that point. So that goes back to following directions. Then from D to E, again, no friction, and it's moving at whatever velocity it had. And then at E, it hits the block, 2. So keeping in mind, this is the velocity of the center of mass, so of the system. So keeping in mind that the velocity does not change of the system or of the center of mass, we keep on going in a straight line. So if you did this and you drop down and you lost and it's moving at that slower speed, we weren't looking at necessarily like momentum. So, but that was only, the nice part of that was only a 1 point loss. So this was an easy question to get like at least 4 points. And the last one, same scenario, but we have a sphere, a ball, essentially. Same thing's going to happen, and we want to know what happens to angular momentum. So thinking of angular momentum, it's going to be L equals I omega. Essentially rotational inertia and rotational or angular velocity, mass and velocity, right? So nothing's changing with the mass, so we're not really looking at the inertia. It's really, is it speeding up or slowing down? But rotationally. So keeping in mind, everything is frictionless except for C and D. So once that plunger moves from A to B, the ball's not going to roll. What would make the ball roll? So thinking about like something on ice or a perfectly smooth surface. We did this as a demo. I think I had those little discs or kind of demonstration blocks going down the whiteboard. And if it was tilted too much, where there wasn't enough friction, it didn't really rotate. It just slid down. It wasn't until there was enough friction that it actually rotated as well. So the answer was C to D, and this was getting your 2 points. This one was kind of hard to get your 2 points. One thing you needed to mention was this first kind of bullet, that torque is needed for rotation. and that friction provided the torque at CD. So if you didn't mention anything about, so if you mentioned it like, oh, it started to, you know, change rotational momentum or angular velocity at CDD, you probably got that at least 1 point. If you didn't mention anything about torque, you didn't get that other point. Also, they specified that you got no point if you mentioned that the sphere decreased in rotational momentum or angular velocity. Because some people are going to think, oh, it's rolling from A to C, and then, right, so it's got both translational and rotational motion, and then it's going to be kind of decreased when you get to C to D. That's not what they're asking for you to identify physics-wise. So again, go back through, look at your questions. Some people requested something again like this for next week. I'm going to post that over the weekend. It is going to be optional. If you want, I'm going to set up a scenario. So if you want it graded, I can grade it for you. It won't count for a grade, but it could be just like another little practice for you. But overall, between both classes, the biggest point losses were not answering the question that was answered of them. If I stuck to the rules of like, oh, Mr. Ford, I submitted answer 1 and 2 because I ran out of time and I didn't know I couldn't use, you know, a link for Google Docs, or I literally ran out of time. Somebody said they couldn't take the picture, or they could only upload 1 picture. So all that stuff is not going to necessarily get you a retake on the real exam, and minus all that's going on in the world right now, if it was like a real thing in class and you ran out of time, you run out of time. All right. Have a great weekend.